Hi, I'm Rick Carter, an application specialist with Agilent Technologies. I'm going to take a couple of minutes to show you how easy it is to create a design in Genesys. Using keyboard hotkeys, I'm going to press L and drag horizontally to place an inductor horizontal in the schematic. Using on-screen editing, I'm going to enter 25 nanohenries for the value. I'm going to press C for a capacitor and drag it vertically to place it vertically. And I'm going to make that also 25 picofarad. If I highlight the inductor and press Control D on my keyboard, I can duplicate it, and if I press F3, it rotates the part into the orientation that I prefer. I press I for an input port, O for an output port. I can hit Z to zoom into the schematic, and then hit G for a ground. I've now completed my schematic. If I press the Go or Run Analysis button, it runs the analysis and creates a data set. All I have to do is right-click on the output port, say Add New Graph or Table, and I immediately see S21. Under Window, I can tile vertically to see both the schematic. I'll press Z to zoom in again, and now I will do a Control A to select all of the parts in the schematic. Under the schematic pull down, I can say Make Components Tunable, and they show up over here in the Tune window. I can select the standard value to tune to standard values, and as I tune the capacitor, you can see it tunes very quickly. I can place a marker to mark where I am and then tune, and it will keep the original value. And you can see it is real-time tuning. I can use the arrow keys or I can use my mouse wheel to tune. I can also right-click on the input and create a graph of S11. If I want to change this to a Smith chart, I double-click on the graph, select Smith chart, and immediately I have a Smith chart. I can tile the two, and as you can see, the Smith chart and the linear graph will tune simultaneously. Genesys packs so much simulation power behind this fun and easy to use interface. Let me show you quickly what it enables me to do. Here we have a simple receiver. I can right click on any node within the circuit and immediately plot a spectrum of that node. I can hover over any point at that spectrum and zoom in, and I can hover over any spectrum and show exactly how that spectrum was created. This is a 460 megahertz spectrum. It's the second harmonic of the source minus the third harmonic of the LO and was created in the mixer. This root cause analysis prevents finger pointing about who is causing the spurious problems. I can also right click on the output and plot many different path type measurements. A path measurement shows the path along the schematic at the bottom, including the nodes. I'm going to show the power before and after the amplifier to show that there's 10 dB of gain through the amplifier. Now I'll tile the graph with the schematic, and I have a minus 10 dB input right now. I'm going to increase that up to about 10 dB, and the simulation is already run, and it's showing me that my amplifiers have been driven past the compression point, and that now my gain is 3 dB. It's reduced because it's in compression, and we show a 3 dB gain in the path graph. New in Genesys 2010 is the ability to use nonlinear circuits at the system level. Here I have our receiver, and on the right I have a nonlinear amplifier called swept power. I can drag this from the workspace tree into my system schematic, and it places what's called a circuit link in the schematic. I'm going to delete my amplifier that I was using before and then drag my circuit link into the circuit and resimulate. And as you can see, it runs the harmonic balance simulation. Our 10 dB gain is going to go to approximately 0 because I have the circuit turned off. You see I have VDC at only a half a volt, so we have no gain, and it's replaced our icon with a circuit link icon. So now I can tune it up to about 3 volts, which turns the transistor on We're running our harmonic balance simulation again, and as you can see, we're back up to about 10 dB of gain. Also new in Genesys 2010 is the ability to use Agilent's new X-parameter nonlinear models at both the circuit and system level. Here I've replaced our amplifier with an X-parameter model. At minus 10 dB input power, you can see we have approximately 10 dB gain through the X-parameter model that's now shown in the path. If I increase the input power to 0 dB, approximately, or 1 dB, we will run the harmonic balance simulation, and because the amplifier is driven into compression, you see we're down to approximately 4 dB of gain. I've shown how to replace the nonlinear blocks within your system simulation with circuits and with X-parameter files. Genesys also includes the widest range of synthesis capabilities in the industry. Here, let me show you how I can synthesize a filter quickly from within our system circuit. As you can see here, this filter is a Butterworth filter third order from 1860 to 2060 megahertz. If I right click on the filter, say synthesize subcircuit as a microwave filter, it immediately opens up our mFilter synthesis tool, gives me a Butterworth filter on the settings tab. It's third order 1860 to 2060, just like we specified at the system level. I can change the topology. I'm going to synthesize a hairpin filter. You can immediately see the schematic converted to a hairpin filter. I'm going to go to the Options tab, select a manufacturing process. We have 13 different processes. I'm going to create a microstrip standard filter. I've already loaded my substrate, and it converts it now to a microstrip design. I can also click here and it will immediately create a layout, which I will show you in a minute. Now our response is not too good at the moment, but I can click on the Optimize button, and as you can see, it's immediately starting to optimize. You can see the starting values and the ending values that we have shown on the graph, and it is updating, and within a very short amount of time, it will come up with a very realizable and very usable filter. Now if I stop the optimization, I'm going to clear the initial response, and as you can see, we have a very good filter. And if we go back to our system level design, the filter here has been replaced. It says these parameters are ignored and the model is disabled. It's using the model, the circuit model that we just simulated. Previously, when I synthesized the filter, I showed how I clicked Create a Layout, which created the layout and prepared it for a momentum electromagnetic simulation. When I did this, it added this Layout tab and created this layout as shown here. Now to perform a momentum simulation, just go into the New Item button, Analysis, and add Momentum Analysis. I'm going to simulate the filter design at 1710 to 2210 megahertz, which is what we simulated over the linear range, and click Calculate Now. Genesys has already prepared the layout for simulation by adding the ports, the input and output ports, and now it's creating the mesh. The simulation completed in under 17 seconds on a dual-core 1.5 gigahertz Pentium processor. And now all I have to do is go into the original graph, add the momentum simulation, select the momentum data, and I can add it to the same graph. And as you just see, we get a very good agreement with the linear simulation. It's a little narrower bandwidth and a little more loss in the passband. Finally, you can view your layout and the current flow within your layout in full 3D and determine if you have any issues with your layout. There are many other easy, fun, and powerful capabilities like these that I'd love to show you, or better yet, you can experience for yourself by requesting a Genesys trial here. Request your free Genesys trial license by visiting this link.